Located about 100 miles northwest of Las Vegas, Yucca Mountain is the most thoroughly researched site of its kind in the world. For more than 20 years, the project has involved extensive scientific study on Yucca Mountain's geology, hydrology, biology, and climate. Experts throughout the world agree that the most feasible and safe method for disposing of highly radioactive materials is to store them deep underground. The facilities you see at the surface are only a small fraction of the science going on deep inside the distinctive ridge. When the giant tunnel boring machine reached daylight at the south portal of Yucca Mountain's Exploratory Studies facility in 1997, it marked a major milestone, the completion of the main tunnel that loops beneath the mountain. In this three-dimensional cutaway view, you can see the tunnel in relation to the surface as it slopes down, then turns south and up toward the exit. This tunnel serves as an underground testing facility, a 5-mile laboratory where scientists and engineers conduct studies on the rock beneath Yucca Mountain. The tunnel will also serve as the main access point to the planned repository. An artist's conception of the footprint, or pattern of underground emplacement tunnels, is shown on this graphic. As you'll see later, the location and spacing of this pattern will be important. Shielded transporters will move radioactive waste containers down the main tunnel to their emplacement tunnels. Let's take a closer look at the facilities, technology, and scientific experiments going on inside the mountain. The tunnel boring machine, also called the TBM, was used to excavate the 5-mile tunnel. The TBM is 25 feet in diameter. The machine, mapping gantry, and trailing gear stretched more than a football field and a half and were custom built for the Yucca Mountain project. Workers drilled and blasted a starter tunnel where the TBM began its work in 1994. The machine gripped the sides of the tunnel so it could push its massive cutter head into the rock. While the cutter head bored the tunnel, conveyor belts moved the crushed rock to a designated area outside. The TBM pulled 13 special rail cars behind it that allowed scientists to study rock samples and take detailed pictures of the tunnels. It tunneled down and into the mountain, made a left turn, continued south for more than 3 miles, and made another left turn, heading up and out of the mountain. In April 1997, after 2.5 years without a serious injury to workers, the TBM reached daylight. But work inside Yucca Mountain was only beginning. At key points along the main tunnel, smaller alcoves and niches have been excavated using drill and blast technologies and a machine called the Alpine Miner. The miner used 2 sets of massive teeth to grind and tear away solid rock. These alcoves are underground laboratories where scientists perform tests and collect data about Yucca Mountain's geologic features. The mountain has been drilled, poked, excavated, and prodded. Massive blocks have been cut from tunnel walls. Many of the tests study how water moves through the mountain and how water might move radioactive particles through the mountain and out to where people live. Alcove 1 was the first alcove to be excavated. Since it is closest to the surface of the mountain, experiments there focus on how rain or snow move through weathered fractures in the rock. It contains a series of instruments inserted into boreholes like these that give scientists information about how rainwater might move from the mountain's surface through fractures and faults down into the rock. Results showed that most water evaporated or moved around the alcove. A small amount, between 3 and 10%, was collected inside. This test and others show that the fractures in Yucca Mountain drain the little water that seeps into the mountain. Knowing where the cracks are allows scientists to design a repository that keeps water away from the waste. That's important, because the enemy of any metal waste container is water. Faults are breaks in the Earth's crust, where blocks of rock on each side are moving, or once moved, in different directions. While there are no faults within the repository, 3 important faults lie beneath Yucca Mountain on either side of the repository block. The last major movement was tens of thousands of years ago, but all repository facilities will meet current earthquake safety standards. Scientists believe the Bow Ridge, Ghost Dance, and Solitario Canyon faults are keys to water drainage in Yucca Mountain. In Alcove 2, scientists have drilled boreholes across the Bow Ridge Fault and are mapping fractures and geologic features to understand how gases and fluids move through the fault. Alcoves 3 and 4 were drilled in a layer of relatively softer rock called non-welded tuff. Boreholes drilled into this rock gave scientists greater insight into how water and gases move through this type of rock in Yucca Mountain and how water may be diverted around radioactive waste. Scientists found that this rock layer retains water and acts as a sort of tin roof above the repository area. Alcove 5 was drilled at the depth of the planned repository, nearly 1,000 feet below the top of Yucca Mountain, for an important test on how heat affects the mountain. Scientists drilled a tunnel of the same size and shape that might be used to emplace radioactive waste. They installed 9 canisters filled with heaters to replicate the high temperatures generated by the waste. In December of 1997, scientists flipped the switch. Over the next 4 years, the air in Alcove 5 was heated to nearly 400 degrees Fahrenheit, almost twice the boiling point of water. All the while, more than 3,000 sensors attached to 10,000 feet of cable measured how water, the air, and the rock reacted to the heat.
Understanding how the heat affects the rock material will allow us to better design both the distance between the tunnels for waste emplacement as well as the spacing of the waste packages in the tunnels.
In January of 2002, the heaters were turned off. Slowly, the air and rock cooled. Monitoring continued during this cool-down phase with the help of a special webcam that showed a live picture of the alcove and its readouts.
What we learned in Alcove 5 is that the rock material responds to heat in the very same way that we expect it would based on laboratory tests that we've conducted. And we find that the changes in the chemistry of the water are as we would expect given the composition of the minerals in the rock. Very importantly, gathering data like this allows you to gain confidence that your computer models are predicting what will really happen.
The Ghost Dance fault is the main fault that borders the planned repository area. Alcoves 6 and 7 were excavated at 2 points along the fault to assess whether it acts as a barrier to water or helps it move along. Tests here confirm that faults can act as a fast pathway to move water away and past the repository tunnels. Even with the wealth of information from the alcoves along the main tunnel, the planned repository block is further inside the mountain. Scientists wanted to learn more. In March of 1998, it was time to bring in another tunnel boring machine. Smaller than its cousin, the Robbins tunnel boring machine is 16.5 feet in diameter. Miners used this smaller TBM to bore a 1.7-mile diagonal tunnel called the cross drift. It begins before the first curve of the main tunnel and cuts across the level of the planned repository from northeast to southwest. This TBM remains inside the mountain at the end of the cross drift, possibly entombed for eternity.
ECRB ingress 50 meters.
This new tunnel allowed scientists to continue testing in the same rock that would house the waste packages. Yet another alcove, Alcove 8, was cut off the cross drift. Alcove 8 is above the main tunnel and gives scientists a larger area to study water flow and seepage. They set up pools of water above cracks and small holes in the floor of the alcove. Scientists filled the pools with precise amounts of water. Then they tracked how much water moved through the rock and into Niche 3, an opening carved off the main tunnel just below. Results here showed that only about 10% of the water moved far enough to reach niche 3. The remaining 90% moved around the niche or into the voids in the surrounding rock. With more than 6 miles of underground working area, safety is a top priority for the Yucca Mountain project. Workers underground are in constant contact with the surface. They carry lights and special breathing equipment. A trained mine rescue team is always on call. Massive fans move huge quantities of air through the tunnel's ventilation duct. The project's commitment to worker safety has resulted in many important achievements. For example, in 2002, the project logged nearly 3 million consecutive hours of work time without a day lost to injury.
I hope you've enjoyed learning more about our Exploratory Studies facility. You might be wondering, how does all of this science fit into the future of Yucca Mountain? The Department of Energy must get approval from the Nuclear Regulatory Commission to build the repository. The DOE will include extensive results of its experiments in a license application to the NRC that would fill several bookshelves. If and when the NRC grants permission to begin constructing the repository, the Exploratory Studies facility will take on another role. It will become the main access tunnel for construction crews and equipment excavating the new emplacement tunnels. DOE plans to use a phased approach. Waste would be placed in completed tunnels even as construction continues in other tunnels of the repository.
The Yucca Mountain project is the first of its kind. Experts from all over the world have broken ground, not only at Yucca Mountain, but in the sciences as well. If you would like to know more about the Yucca Mountain project, call us on our toll-free number, or you can find us on the World Wide Web at www.ocram.doe.gov.